Hello and welcome to Video Notes 5.3, where we're going to talk about difference of two samples between two groups. So we already know from last unit how to find a confidence interval for a mean of a quantitative sample, quantitative variable, and we called that a one sample T interval. Remember, we used T because we did not know the standard deviation of our population. That will still be the case today. So now we're going to talk about what happens if you grab two independent samples and want to know if there's any difference between these two populations that you drew those samples from. So for example, a teacher wants to find and see if there's two different versions of a test are actually equally in difficulty, or if one of them is harder than the other. She has 120 students, which she randomly sorts into two groups of 60. The scores for version A and a mean of 74.9% with a standard deviation of 8.7%. The scores for version B had a mean of 77.1% with a standard deviation of 5.6%. So the observed gap we're seeing between these two is 2.2%. Okay, if we take the difference of those two scores there, 77.1 minus 74.9. But we know that there's bound to be sampling variability. And so what we want to know is the difference we're seeing here something we could see here just by random chance, or is it that we could maybe never see something like a 2.2? It's very unlikely for that to happen. So why don't we go ahead and start by checking our conditions. It's literally the same conditions as a two proportion Z interval from last class. So why don't you go ahead and take a moment to write down your conditions and check them off. All right, so here's what I came up with. So that new condition independent groups, I checked that off first. We're going to assume that's the independence between the two versions is totally okay. But mostly because there's no reason to believe, and based on the wording of everything, nobody took both versions. That's where things could get a little bit iffy with this. It does say that the students were randomly assigned the version. So this isn't a group of 120 that's random, but instead we did randomize who got what versions. And I think it's safe to assume independence here. That's not any scores are going to be sort of different in affecting each other. So the scores are independent of each other. And the central limit theorem comes to the rescue here because it is larger than 30 that our sample size is. So we can assume normality. So now let's go ahead and move on to doing some calculations here. So first, we got to have our observed difference between these two things, which we already did here. We're going to go ahead and use the subscripts of x sub b and x sub a, x bar, which is going to represent our different versions of b and a. So the observed difference here is going to be that 7.7%, just like 2.2%. I got myself confused here. 2.2%. And we're going to go ahead and define our variables here, where x bar sub a is mean score of version A, and x bar sub b is mean score of version B. Okay, and then what we need to do is do our standard deviation. Well, not really the standard deviation here, standard error, because we're dealing with instead a sample. We're dealing with the sample's standard deviation, so we're going to end up calculating our standard error here. How do you do that? It's the same as last time. We're actually going to combine the variances together and then take the square root of that. So in order to find our standard error here, we're going to find the variance of each one, and the variance in this particular case is going to be s sub x sub b squared over n sub b plus s sub xa squared over n sub a. You'll notice that those are each the square of the standard errors that we usually are performing here. And then we're going to take the square root of all of that. If you ever forget that, remember, you don't have to worry about memorizing it because it is on the formula sheet. If you go to the back side of your formula sheet and looking down at the parameters of a sampling distribution, you can see for two populations, right here, this row, that it tells you exactly how to find those things. If you know sigma, then you would use this one here. In this case, we do not know sigma, so that's why we're over here. You can see that it is the formula we're using there. The square of the standard deviation over sample size in both cases added together to get us that, and then we square root it. So let's head back on over and calculate this. This is going to be the only time we calculate this by hand. We're going to let our calculator do it all for us. So we have, that's the sample standard deviation for version B is 5.6, and 60 people took that. Sample standard deviation for the version A was 8.7, and 60 people took that. And then we'll take the square root of all of that there. So when we actually do calculate it out, if you want to do it by hand just to see if you match, you can pause. Otherwise, I'm going to reveal it. It is 1.3357. All right, we almost have everything here, except we're missing the degrees of freedom. We need to know our degrees of freedom in order to help us find out, like, what is our t-star value? And in this particular case, it is not just subtract 1, because we're actually dealing with multiple variables. If you've read the next paragraph, you now know that it is a bananas formula for it. I mean, it's not totally bananas. If you really want to Google it and try to find it, go for it. But it is not something that we are going to actually calculate here. And in fact, what's weird is it's going to give you decimally answers for your degrees of freedom, which doesn't make a whole ton of sense either. And so your chart actually becomes completely useless. Your t-table, it doesn't have decimally answers. So it turns out this one is 100.73. Your t-table does not have 100.73 along the left column there. It has 100, so you could probably come up with a pretty good value, but we are going to let the calculator do the work for us here, okay? So now we're going to get down into finding and interpreting a two-sample t-interval. And there's the formula for it there. So we've got our difference of our x bars from earlier. The calculator is going to calculate our t-star value for us, and we have our standard error that will help us out as well. But now let's go over to the calculator and figure out how to do it. Let's take a look at how to find a confidence interval for a two-sample t-interval here. We're going to hit stats and over to tests like we usually do. And we're going to scroll on down until we see two-samp t-int. That is the letter or the number 0. So you can also just hit 0 if you recall that, or just arrow down. And like our t-tests and our t-intervals from before, this one has options. We can put in some data, like in our lists, and do it. Or perhaps they just gave us sort of the summative stats from the two different groups. That's the case in this scenario. We don't have lists of data, we just have the different stats. So we're going to arrow over and hit stats. And it's filled with a bunch of random stuff here, but we're going to clear this out and fill it in. So our first group that we are going to fill in here is the it's going to be the group B is what we did first here. So we're going to go the difference the average for group B, version B, was 77.1% with a standard deviation of 5.6%. And in that group was a total of 60. So that's version B. I'm putting it in the same order that the subtraction is in. Okay, if you did version A first, you did x sub A minus x sub B, then you would do version A first. And then our version A was our group 2 here, so that was a mean score of 74.9% with a standard deviation of 8.7%, and there's also 60 in there. And our confidence level is 95%. Down here, we have this option to pool, yes or no. Unlike with proportions, where it automatically pools for us, here it will not. And We do not. We want no pooling. Keep that in mind as we go through. No pooling for this at all, okay? Leave it exactly at no. Never touch that ever, okay? So now we are going to go in and calculate. And there it is, negative 0.45 to about 4.85, it looks like. And look at that, the degrees of freedom are bananas, like I said. So 100.72 or 73, which doesn't make a whole lot of sense, but that's what they are. So go ahead and write down this interval and let's jump back. All right, so we've got our confidence interval, which is from negative 0.45 to 4.85. And so now we are going to have a little interpretation. So why don't you go ahead and pause the video, interpret, and that'll be the first thing we'll discuss when we come into class. All right, so that finishes up the front side. Let's talk about the back side now, where we're going to talk about hypothesis test, just like we did last time. So in this case, we're going to be talking about a two sample t-test. So we want to use this to figure out, is there sufficient evidence to see if there is a difference between two groups? So in this particular case, we're going to look at some stuff about eyes. So myopia is the medical term for nearsightedness, is scaled in units called diopters, which are measurements of optical lenses power. Severe nearsightedness is considered to be anything more extreme than negative 6.0 diopters and becomes considered extreme nearsightedness when surpassing negative 10 diopters. Random samples of patients are drawn from two large optometry clinics that focus primarily on severely, extremely nearsighted patients. Based on the data shown below, with negative signs removed for simplicity, is there strong statistically significant evidence at an alpha level of 0.01 that there's a difference in the average optical lens power of all patients at the two clinics? So let's go ahead and go through our steps that we usually go through here, which is state, plan, do, and conclude. So first we state. Our state is that we are going to be doing a hypothesis test in which our null hypothesis will indicate that we believe there's no difference between these two things, which in this case we're going to call mu sub x minus mu sub y equals 0. We're using mu because right now we're talking about the whole population of these different patients at these different clinics, okay? Not just our data that we have right here. That would be x bar that we'd be using, like we did with the confidence interval. The alternative hypothesis in this case, the wording says is there a difference? So it doesn't say whether we think X or Y clinic has greater. So we're going to just say that's mu sub X minus mu sub Y is not equal to 0. Where mu sub X is average optical lens power at clinic X, and mu sub Y is average at clinic Y. I'm not going to restate the whole context for that second part because I've already stated it there. That is totally fine to do. All right, time to do. We are doing we're on the plan step. We're going to do a two-sample t-test. And what we need to do now is check our conditions. Pause the video and check your conditions here. All right, so you should have checked 4 conditions. I'm going to leave it blank, and if you forgot that there were 4 this time around, go back and fix it. What we're going to do now is we are going to jump to our calculator to do the do step. As I've noted before, the calculations here are getting messier and messier, and so it's really important that we think about how to use our calculator to help us through that messy calculations and really focus on the stats. And so the things you need to give here is always these three things. You need the t-value, you need the degrees of freedom, and you need a p-value. And your calculator can give you all those things, and you can write it in a way that makes sense and kind of incorporates all of it. So why don't we jump over to the calculator, see how it provides us our details, and then we'll come back and write down our answers. Let's see how we do now a two-sample t-test. So because we have data, we should go in and put them in our lists here. So you should pause the video if you haven't done that already. Something to note is that you might have noticed on my video that I crossed off the first value for clinic Y, which was 13.75. Do that too, cross it off. The first data value you should plug in is 1.50 for clinic Y, which means that we're only gonna end up with a grand total of 13 data points for that, I believe. 15 data points for that. So go ahead and plug those in. And then we're gonna go over to stats, tests, and we're gonna scroll on down until we see two samp t test, which is number 4 here. So press enter. And this time around, we are not given the summative stats, we have data. So we're gonna click over to data and press enter. And usually it's sort of set up like this: list 1, list 2. Yeah, I'm doing clinic Y minus clinic X minus clinic Y. So that's gonna be good here to keep that in mind. And we just wanna know if they're different. We're not interested in whether X or Y is larger. Pooled? No. Remember, no pooling here. And here we can calculate or draw. It's your choice. I'll press calculate this time. And you can see that it gives us the things that we need. Our t-value, you can write that down. Our p-value, you can write that down. Our degrees of freedom. Those are the 3 pieces of info that your tests need in order to be full credit. So write those down, and let's head back over and conclude. So as we saw from our calculator, we have this. So we need t, degrees of freedom, and p-value all written in here. And you can see that I have done that. I have actually a subscript on my t, so that way it includes the degrees of freedom. If you just want to write t equals, great. Then you should have an extra thing over here where it says df is equal to, and have that written separately if you're not going to include it as a subscript. So this is all you need. You need to let the calculator do the work for you here because, like I said, it's getting messy. At this point, I think you can jump over to writing down your conclusion. We're going to end the video here. You are responsible for a couple of conclusions and some conditions, and be ready to extend your thinking a bit about the further questions we can ask tying together confidence intervals and hypothesis tests. We will see you in class.